Trigonometry, Chapter 6, Inverse Circular Trig Functions and Trig Equations. Section 1, Inverse Circular Functions. Video 2, Determining the Domain and Range of Inverse Sine. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, we reviewed the algebraic concept of an inverse function. If a function f of x is 1 to 1, in other words, its graph passes the horizontal line test, then there exists an inverse function f inverse of x such that, number 1, f of f inverse of x equals x, and f inverse of f of x equals x. This means that the functions undo each other. Number 2, the domain of f of x equals the range of f of x. The domain of f of x equals the range of f inverse of x. This means whatever goes into f comes out of f inverse, which is important for this second composition statement because this x initially goes into f, hence must be in its domain, but must also come out of f inverse and hence be in its range. And number 3 is just the reverse. The range of f of x equals the domain of f inverse of x. Again, that means that what goes into f inverse must come out of f, which is illustrated by this statement up here. This x goes into f inverse and therefore must be in its domain, but it also comes out of f of x and therefore must be in its range. The graph of y equals f inverse of x is the reflection of the graph of y equals f of x across the diagonal line y equals x, and to find f inverse of x, we solve x equals f of y for y. So we switch the x and the y, and then we solve. In this video, we closely examine the inverse of f of x equals sine of x in terms of domain, range, and graph. Let's start with the graph of f of x equals sine of x. Now, its domain is negative infinity to infinity because it goes forever in both directions, and its range is from -1 to 1, low to high. Now, if we were to check the horizontal line test here, we would have a problem. Because of the periodic nature of sine, this graph miserably fails the horizontal line test. Any horizontal line that intersects it will intersect it an infinite number of times. Little typo there. As such, the function does not have an inverse function unless we restrict its domain. So in other words, we chop off a piece of the graph. But this raises the question, what is the largest part of this graph we can keep that still passes the horizontal line test? Now, there are multiple places to find this largest part, but we're going to use this part from negative pi over 2 comma negative 1 to pi over 2 comma 1. Because notice that this part of the graph, well, a few things. Number 1, as x values, it includes values that represent quadrant 1 from 0 to pi over 2. But it also includes values whose sign is negative between negative pi over 2 and 0. Extending this graph further in either direction will violate the horizontal line test. Once we hit the high point and turn around and start coming down, that little hump is going to violate the horizontal line test. Same thing over here to the left. Thus, in order for f of x equals sine of x to have an inverse, we must restrict its domain to negative pi over 2 to pi over 2. Notice that the range is still -1 to 1. To get the graph of the inverse, we will reflect this along the line y equals x, and it'll turn out to look like this. See it flipping? From this, we can see that f of x equals sine inverse of x has a domain of -1 to 1, which makes sense because it's the range of this function, and a range of negative pi over 2 to pi over 2, which again makes sense because that's the domain of this function, the domain of the range switch. So that's the domain of the inverse sine function, and that's its range. Now be careful. Saying f of x equals sine inverse of x has a range of negative pi over 2 to pi over 2 is different than solving a trig equation. For example, as a function, sine inverse of square root of 2 over 2 equals pi over 4 because sine of pi over 4 is square root of 2 over 2. However, the equation sine of theta equals square root of 2 over 2 has more solutions than theta equals pi over 4. In other words, we can't just hit sine inverse on both sides of this and go pi over 4. It's periodic. There's a lot more solutions. This has an infinite number of solutions. Any number of the form theta equals pi over 4 plus 2 pi n, or theta equals 3 pi over 4 plus 2 pi n is a solution for any integer n. Just a reminder about what these things mean. The plus 2 pi n means the 2 pi is one revolution, and then times n means however many revolutions we want. So if we were at pi over 4 and added a circle, we're coterminal to pi over 4, and it doesn't matter if we go forwards or backwards. Now, 3 pi over 4 is the other solution to this equation, but that one is in quadrant 3. Recall that quadrant 2. Recall that sine is positive in quadrant 2. Does this look familiar? So if 45 degrees works as an angle in quadrant 1, then if we put 45 degrees as a reference angle in quadrant 2 and then measured it from standard position, that would be 135 degrees, or 3 pi over 4. So this represents the solution in quadrant 1 plus as many revolutions as we want, and this represents the solution in quadrant 2 plus as many revolutions as we want. But as an inverse trig function, because it's a function, it can only return a single value. So sine inverse of square root of 2 over 2 would give just pi over 4. So there's a difference between evaluating an inverse trig function versus solving the corresponding trig equation. Think of sine inverse as being a button on a calculator. It can only return a single value as an output. That value will always be in the interval negative pi over 2, pi over 2. There's no now you try for this video. Don't worry, there will be some soon.